Then the same projection we followed for a single particle. We did its kinematics and we did the kinetics. We did the balance laws, the balance of linear momentum, the balance of angular momentum. Then we also did the integral forms of the balance laws. Then we did the work energy theorem. And we did the same thing for a system of particles. We're going to do the same thing for rigid bodies. So we've talked about the balance laws for a rigid body last week. The balance of linear momentum, F equals MAC. The balance of angular momentum, the three forms above the center of mass, about a fixed point O if it exists, or about any point P. And then today we're going to talk about the integral forms, the time integral forms of these balance laws, the linear impulse linear momentum equation, the angular impulse angular momentum equation, and the conservations of linear momentum and angular momentum. On Thursday, we'll talk about the work energy theorem for a rigid body. And then next week, which is going to be our final week, we're going to have Tuesday's lecture. We're going to solve problems, review. If you have questions, you can we can answer them on Tuesday, and then on Thursday we have our final. Is that good for our concluding plan? Okay, you have a homework that's due today, and today we're going to post a homework that's due on Tuesday, and that's going to be your final homework. Okay, great then. So just let's remember the balance laws and write their integral form. This is an interesting demo about the conservation of angular momentum. Okay. Okay, so you can guess this. For the linear impulse linear momentum equation, we're going to integrate the balance of linear momentum. So the integral of f dt is g from t1 to t2 is g of t2 minus g of t1. What is the linear momentum of a rigid body? For a rigid body, g is equal to what? mv, the velocity of which point? The velocity of the center of mass. Great. So that's the linear impulse linear momentum equation. Then we have the angular impulse. So we'll have two forms, about the center of mass or about a fixed point O if it exists. We won't do the angular impulse angular momentum equation about a random point P because it's just not as easy to integrate. So about the center of mass, we have the integral from T1. Again, the balance of angular momentum about any material point P on the rigid body is difficult to integrate, not as straightforward, I'm not sure if we can integrate it even and have a nice expression for that. So we'll only write the angular impulse, angular momentum equations about the center of mass C and about the fixed point O if it exists. And then, any questions? About conservations, when is the linear momentum of a system of a rigid body conserved? So under what conditions is the linear momentum of a rigid body conserved? Exactly, if the external forces. Okay, can someone think of an example where the linear momentum of a rigid body is conserved? Yes.
So, like an object flying in space?
Yes, exactly. If an object is flying in space, then there's no gravity, no weight, no forces acting on the rigid body. Its linear momentum is conserved. The velocity of the center of mass is going to stay constant. And then, as we did for particles, the linear momentum could be conserved only along a certain direction. For example, if you have a projectile on Earth, then the linear momentum is conserved along which direction? The horizontal, right? It's not conserved along the vertical where you have the weight force. Okay. And then when is the angular momentum of a system conserved? Under what conditions is the angular momentum of a system conserved? Exactly, when MC, about the center of mass, for example, when MC is equal to 0. Can someone think of an example of a motion where angular momentum is conserved? Yes. If an object is rotating in space, right, exactly, no moments are acting on it, then its angular momentum is going to be conserved, and its angular, if so for an object where angular momentum is conserved, does that mean that omega is constant? Okay, I see a no. Okay, what do you guys think? Why no?
The linear momentum can be conserved, like using the ballerina example, which looks like the momentum or velocities.
Exactly. So what your friend is saying is that the angular momentum is the inertia tensor times the angular velocity. So if the inertia IC is conserved and this is conserved, if both of these are constants, then omega is going to be constant. Like the example your friend gave of a rigid body in space. However, if consider, for example, a body that's not rigid, like what we're going to see in the demo, it's actually composed, it's a system of rigid bodies, but the configuration of the system can change. So the inertia tensor changes, the mass distribution changes, so the angular velocity is going to change. So consider this demo here. Okay. Consider this demo here. Say that this Hoberman sphere is rotating. If we compress the Hoberman sphere like this.
You can expand it and contract it using this
So when we do this expansion or contraction, what are we actually changing? The inertia, the mass distribution of the sphere. So if this sphere is rotating and we're pulling down on this cord to change its configuration, the sum of moments about its center of is going to be 0. So is the angular momentum of the sphere conserved? If all we're doing is we're pulling on this cord that passes by the center of the sphere, is the angular momentum about the center of the sphere conserved? Yes, because the sum of moments about the center of mass is 0. So the angular momentum is going to be conserved. But is the angular velocity going to be conserved if we change the configuration of the sphere? No. What's going to happen when the sphere shrinks? Is it going to go faster or slower? Faster. Right, because its inertia is less.
String. What I'm going to do is to use it to demonstrate this. This is also denoted by the string that passes vertically through the sphere. We will note first that the moment of inertia in this contractular momentum in the expanded high moment of inertia configuration, and then we contract it, its angular speed should increase.
Wow. Okay, so that's what we predicted. Nice.
And sure enough, it's one of the momentum.
Cool, right? Any questions? There are many such demos. I just searched for this, but if you look at this, so what this guy is going to do, that's the ballerina example, kind of.
It's your dad. Shoot.
Okay.
Of the conservation.
So this person, he's going to step on this stool, and he's going to rotate, and we're going to assume that everything is frictionless. So there's, as the stool is rotating, there's no kind of resistance moment. Ooh, we're cutting off. One more time. Okay. It's fine. We got the idea. There are many examples of this online. You can actually see, search the video of an actual ballerina changing her angular momentum. Okay, he's here.
Okay.
And that's going to be the subject of your, when he changes his...
You can see my tie flying up. So...
That's going to be the subject of your last homework. We're going to solve a problem like that, and we're going to do a simple animation of basically a dumbbell with two masses, and the dumbbell is rotating. What would happen if we're shrinking the distance between the two masses? Maybe let me actually Google ice skater angular momentum. Maybe this video.
If your spins get faster when you fold your arms, you're an ice skater. Here's why this happens. All right, so picture an ice skater spinning.
Okay, I'll let you watch these videos before I shut this off. This is a nice video by Professor Walter Lewin from MIT. He's a physics professor, maybe you've heard of him. He does a lot of demos, and this one is about basically the moment of inertia. So what he does in this experiment is that he rolls cylinders with different moments of inertia down an incline. Where are the cylinders? Like this and this, having the same radius but different mass distribution, so different moments of inertia. And you can guess which cylinder wins the race depending on the moment of inertia of the cylinder. So basically telling you that the mass distribution matters. So that's an interesting video to watch. I will link it in the course website. Any questions? Okay. So then our plan for the rest of the lecture is to solve as many problems as we can from set 22. And if we have time, we'll introduce the kinetic energy of a rigid body at the end of the lecture. Deal? Okay, so pull up your set 22, please. I have a few hard copies here if you want, if you need any. So this is 22. Okay, let us see. Okay. just sorry. I guess this is 23. This is 22, 23, 23, 22. Okay, I'll take one also. And let's look at the first problem. Please take a couple minutes, start solving the first problem with your neighbor while I erase the board. So problem 1, 613A. Okay, a person who walks through the revolving door exerts a 19 Newton horizontal force on one of the 4 door panels and keeps the 15-degree angle relative to a line which is normal to the panel. Okay, again, a person who walks through the revolving door exerts a 19 Newton horizontal force on one of the 4 door panels and keeps the 15-degree angle constant relative to a line which is normal to the panel. Each panel is modeled by a 60 kilogram uniform rectangular plate, which is 1.2 meters in length, as viewed from above. Determine the final angular velocity omega of the door If the person exerts the force for 3 seconds, the door is initially at rest and friction may be neglected. Okay, so how are we going to solve this problem? Any ideas? Yes.
With the first equation for angular momentum about the center.
Exactly. So in this problem, if we look at the system, if we take our system to be the 4 panels, it happens to be that the origin or the center of mass is basically a fixed point. The 4 panels are rotating about their, combined center of mass. So if we consider so the center of mass is a fixed point, we can apply the angular impulse, angular momentum equation to this system. The integral of m(o) dt from t1, so basically from 0 to 3 seconds in this problem, it's ho at 3 seconds minus ho initially. What is the initial angular momentum of the system? 0, because omega is 0. So this is 0. The system starts from rest, omega is 0. What is the angular momentum or the expression of angular momentum at t equals to 3 seconds? Right, I-O omega. Now here omega is along EZ, and expressing this in terms of a basis, I can put a co-rotational basis in here. These planners are perpendicular, so I can do this. The products of inertia here, are they 0 or non-zero? Well, let us first write that's I-O x z omega ex right? That's the angular momentum of the system. We need to find I-O-X-Z, I-O-Y-Z, and I-O-Z-Z from the geometry. Do you have your inertia tables? We do not know that, but I don't think we will need that information.
Just like slender rods.
Well, they are uniform plates rotating above their end. Check in the inertia table. Do you have a kind of a uniform plate?
We have only 4 rectangular.
Yeah. Okay, the rectangular shape. If you take one of its sides to be 0, you'll get the rectangular plane.
Oh.
Do you need the length of the rectangle? Yes. Yeah, the thickness is equal to 0. The height will be the equation. So from your tables, if I have a plate like this, what are the given dimensions of the rectangular parallelepiped? What are the dimensions in the tables? L, A and B. Okay, and let's take this to be the z-axis. What is ICZZ?
112 and
A squared plus L squared.
yeah, but 112
Okay, cool. So then in our case, for this to be a plate rotating above the z-axis like that, which dimension should we take to be 0? If we take, yes, well, yes, we're going to take A to be 0. Okay, so again, let's do this step by step. We gonna apply the angular impulse, angular momentum equation. We found the expression for the angular momentum. We're gonna need to find the inertias. To find the inertias, each door panel is modeled as a plate. So we looked at an inertia table, and we can kind of deform or take one dimension of the parallelepiped to be 0, and we'll get a plate. So if this is our shape, if we take A to be 0, then we'll get a plate. Here B is going to be the length of the door, but it's not entering into our calculation, so we do not need to know that. And L is the 1.2 meters. That is this length. Okay? Because of symmetries, what will the products of inertia be for each cylinder, for each door about the center of mass of the system? 0. They're going to be 0. By the way, you can think of this door as being composed of 4 panels, 1.2 meters wide each, or you can think of them as being 2 panels, double the length, right? So for these 2 panels, the center of mass of the panels also coincides with the center of mass of the system. And that might be easier to think about that when saying that the products of inertia are 0. Now for IOZZ, actually if we think of 2 panels, then what is the moment of inertia of the system about O? If I'm thinking of 2 panels, I'm going to take 1 over 12, 2m, and then the length of one big panel is 2.4 meters squared, right? And that's going to be the same for the other panel, so I'm going to multiply that by 2. There's gotta be questions about this, so think about it, take a few seconds, and then let me know if you have any questions. Yes. Yes. Yes, both of them. Yes, I'm adding just the ZZ component, and they both have the same distribution about that mass distribution about that axis. Yeah. Any other questions? Questions? Okay, what do we still need to do? The integral, yes, we need to calculate the angular impulse. Before we calculate the integral, let's calculate the moment, MO. So how do I calculate MO? The moment of this force Fa, all the other forces, they basically pass by O, kind of, no, they don't have a moment about O. How do I calculate the moment of the force Fa? Product of what plus what? R and Fa. So that's going to be 0.8 Ex crossed with Fa, and Fa is always forming this angle 15 degrees with Ey basically. So I can say that Fa, how can I express it in terms of the corotational basis? How can I express Fa in terms of the corotational basis? Yes? Do we agree? Raise your hand if you agree with this. Okay, cool, awesome. And I can take the cross product. That's going to be 0.8 times 90 times cosine 15. Easy. So the Ex component doesn't matter really. So if you're in this situation, just push the door perpendicular to it. Okay. And that's constant throughout the motion. So if I integrate MO dt from 0 to 3, I'll just multiply MO by 3 because MO is constant. Its magnitude is constant and its direction is constant. EZ is constant. So that's 3 times MO. So plugging back everything into the equation, and the integral from 0 to 3 of MO dt is H O at equals to 3, so that's 1 over 12 2m 2.4 squared times 2 omega at t equals to 3, and then the integral of MO is 3 0.8 90 cosine 15 degrees easy. And basically, we've solved for omega at t equals to 3. Any questions? Okay, let's look at problem 2 then. Any questions before we move on?